Lesson 6 is on thermochemistry. This is the relationship between energy and matter. I always start with this lesson by looking at the lab and what you're going to be doing in lab. So this kind of lets you plunge into the subject before you get all the details of the background. In lab, we'll be doing two parts. In one part, you'll put a hot metal into water and you'll keep track of how much the water warms up. In the other part, you'll put a chemical reaction in the water, and again, you'll watch the temperature change of the water. We're going to start by considering the hot metal. Okay. When you put the hot metal in the water, heat will leave the metal and go to the water because the water is cooler. So Q is how we, the symbol we used for heat. Q means heat. Q can be positive or negative. Negative Q means losing heat. Q will have a number. It'll be a number of joules or kilojoules usually, and that number will be negative for something losing heat. Q will be positive if something is gaining heat. So in this case, Q would be negative for the metal and positive for the water that's gaining heat. Again, Q will be a number of joules or kilojoules, and it'll be positive or negative. Let's see. So the relationship is the Q for the metal is going to be the same number and opposite sign as the Q for the water. So this is what that means. Whatever number we have for the water, if we change the sign, we'll have the Q for the metal. Okay. Don't confuse heat with temperature. Heat gives a temperature change. Heat is the transfer of the thermal energy. Specific heat, sometimes called specific heat capacity, small letter S, is how much heat it takes to raise the temperature of something. In other words, some substances will warm up with very little heat given to them, and other substances don't warm up so easy. They have to absorb a lot of heat before they warm up. Here's an equation that relates that, that kind of rearranges that. Q is heat. The specific heat here is the physical property. M is the mass of the substance that's being heated, and delta T is the temperature change of the substance that's being heated. This would work the same if it's being cooled, by the way. But delta T is T2 minus T1, or T final minus T initial. This delta T term can be positive or negative. It's negative when the substance is cooling and positive when the substance is heating. And that's how the Q ends up getting its positive or negative sign. Okay, so let's think about how specific heat works. It's how much energy it needed to raise the temperature of a substance. So for metals, do they require a lot of energy to be warmed up? No, so their specific heat is a smaller number. And then what about water? Water is kind of known for its specific heat. It takes a lot of energy to warm up water, so it's considered large. And just to give you an idea, you don't have to memorize this. It'll be given to you on your tests and stuff. But the specific heat of water is about 4. So for metals, it's in the range of 1 or less. It's good to know what's a normal number for these to come out for your answers. Okay, let's look at an example problem. Here's an example problem from lab. Again, this is where you have a metal that is in water. The metal is hot, so heat is going from the metal to the water. We'll know how much water we have. So this is the mass of the water, and the water's temperature is changing. So I've got a temperature of water and another temperature of water, and then I look closely and let's see. So this is a T1 and this is a T2. And then I have this mass. This is the mass of the metal. And this temperature is a temperature of the metal. And is that a T1 or a T2 for the metal? Well, it looks like it's what it starts off, so I'm going to call that a T1 for the metal. Okay, first we'll focus on the water. We have more information about the water. The equation that we use is that Q, and we're looking at the water, equals SM delta T. And when I plug in my numbers here, I need to make sure that I'm using the numbers for the water. So plugging in the specific heat of water, the mass of the water, T2 minus T1 for the metal, or for the water, okay, and you can see where our units are going to cancel. This is, there we go. The degree C will cancel, the grams will cancel, and we will be left with joules. Really watch for that, because in some problems we'll have kilojoules and some problems will have joules. So in this whole lesson you'll need to kind of keep track of which one you're dealing with. Before I multiply this out in my calculator, I need to do this step. Always look at your delta T first and see what happens to your significant figures, because on this one, as in many, you're losing sig figs when you follow that subtract rule. And so if I skipped that, I would think my answer would have 2 sig figs. But look at this, it drops down to 1 sig fig. So I'm just going to have 1 sig fig in my answer, which is not very many. But a lot of these end up that way. So watch for that. Okay, so my answer comes out in joules. So that's how much heat the water absorbed based on its temperature change. So how much heat did the metal lose? What's the Q for the metal? It's the same number, opposite sign. Okay, so what's the specific heat for the metal? We can go back to this equation, except use all the numbers for the metal. So I don't have a lot of room, so I'm going to write it over here. The Q for the metal, we already said. The specific heat for the metal is what I'm solving for. The mass of the metal was given in the problem statement. I need the delta T for the metal. And I was given a T1 for the metal. Running out of room to see. What do I use for T2 for the metal? Well, the assumption that we make is in the lab is that we put the hot metal in the water and we let it sit long enough until the temperature of the metal is equal to the temperature of the water. That's what we call thermal equilibrium. That's when heat is no longer transferred. Okay, so, in other words, T2 for the metal equals T2 for the water. And so it is 29 degrees Celsius. Okay, and we plug that all in, we get a specific heat of 1 sig.